All right, so today we're going to talk about light. Light is special to us because it has a very important role to play in our lives. And one of the basic introduction to waves that we see is usually either through wind or light. So, how does light work and how do we see things? So, the idea here is that light has these sources. So, there are sources of light. Okay. And that source will emit light. So it gives light off. And there's going to be some sensor, something that can detect light. So this source will give that, and the sensor will detect that. Okay. So this emits and sensor detects. So when we see things, we usually see them when the light is given by a source and our eyes are acting as detectors, these sensors. So it's not that we directly get it, because if the sensor were to directly look at the source, then the amount of light that comes might damage the sensor. Okay. So that is why, for example, if there was this box here and something was able to, we were able to see this, it's because the source gave the light and the sensor, that is our eyes, detected it. The sensor doesn't have to be just eyes. It could be a camera. It could be something else. Okay. And few sources that we know of are light bulbs or lamps or sun, stars. Moon is not actually a source, but how moon works is that it works as a very good reflector. So it reflects the light of the sun that we get, and that way we are able to see it. So basically, this thing has to reflect light for us to see it. If it does not reflect, then you wouldn't be able to see it, because if it doesn't reflect, then there's no light that is coming to the sensor. So that way you will not be able to see it. So if you want to see things, those things must reflect light. If they don't do that, so for example, if they're very dark, then that means they're going to absorb light. So what do these sources do? They can absorb, they can reflect, or they can refract light. So in these three cases, the way we see things are going to be slightly different. So for example, if you look at a mirror, then what a mirror does is that it has been polished on one side so that it reflects most of the light that falls on it. It does absorb light to some extent, but most of it reflects it. So we are able to see it. Similarly, if you look at a glass, then it refracts light and some of it is reflected. So if there's a glass here and light comes in, then some of it is reflected, and you know that the angle of reflection incidents are the same, and some of it is refracted, which then goes away. The reason you're able to see this is that you're able to see that there is some mismatch of angle happening. There is some light being reflected. So if this is your eyes, there's some light being reflected, but some of it is not given off. So this difference in light, or the amount of light, you're able to categorize this, that all right, this that thing is there and it is not entirely translucent. If something were not to reflect any light, then you wouldn't be able to see it. If something were to reflect all of the light, then it will appear quite shiny, probably as shiny as the source, because it's reflecting all the light that is there. Some things, when they absorb light, they convert it to some other form. Like when they absorb light, they convert the light energy to some other form of energy, like heat energy. And that is how some solar cells might work, that they take the energy, they convert it to heat energy. So light, just like any energy, can be converted to others. And that is how we can create electricity from uh, sunlight. So basically, our topic of discussion today is light, how we see things, and how light waves work. Okay, so light is a transverse wave. In fact, it's a special kind of transverse wave. We call it electromagnetic wave. So let me just give you an idea of what an electromagnetic wave is and how it is different from other waves. So electromagnetic waves are special because what they do is that, let's suppose you have a wave traveling in this direction. And if that's the direction of the wave, then it has an electric field that is parallel, that is going up and down, which is parallel to the direction of the transfer of wave. And it also has this magnetic field that is going like this, which is also perpendicular to the wave transfer. So here's the thing. You have, this is the where the wave is going. This is the direction of electric field. Okay. And this is the direction of the magnetic field. And that is how this is also 90 degree to both of them. So we have three perpendicular or orthogonal fields. There is one way in which the wave is going, one where the electric field is, and one where the magnetic field is. It is the combination of these fields, and they don't interact with each other as much, but it's the combination and the effect of these that light does not really need a medium because it doesn't rely on any external particle. Light has its own particles to carry this energy, which we call photons. Okay. So they are the ones that carry this energy. Now, when it travels, the main idea here is that because of these photons, it's able to travel where you don't even have a medium. So because of these photons, EM waves or electromagnetic waves can travel through vacuum. And the reason is simple. Vacuum is where you don't have any other particles. So any wave that depends on other particles will need to obviously have a medium. But because light has its own particles, it doesn't need any other external medium. So it's able to travel where there are no particles. So it can travel through vacuum. Now, the two things that change for electromagnetic waves are the frequency and the wavelength. And they are inversely related. So if the frequency increases, wavelength decreases. What does not change is the speed. So the speed is a constant. In air, so speed is constant. In air or in vacuum, the speed is seen, which is 3 into 10 power 8 meter per second. Now that is the speed limit of the universe that we live in. Nothing that we have seen so far, no material thing, can travel faster than speed of light. There are things that can travel beyond the speed of light, but those are not like matter nahi kar sakta, messages kar sakte hain, information can travel. There are other quantum effects that we see that can happen beyond the speed of light, but material particles, they cannot travel beyond the speed of light. See, so this is our cosmic speed limit. This is zyada hum nahi kar sakte. This might seem like a lot, but it's actually really, really slow compared to the scale of the universe. So, for example, sun, which is right next door, like it is the nearest star that we have, light takes 8 minutes, 20 seconds to get from sun to us, despite it being really, really fast. हमें लगता है कि बहुत ज़्यादा speed है because moon पे जाते हुए from moon to earth, light would take 1 minute, right? So, 1 second, which isn't much. It's good. Lekin moon is really next door, bilkul saath hai. ठीक है? The distance of moon is nothing compared to the scale of the universe. So, अगर यहाँ से light ने, let's suppose, next star पे जाना है, which is just 2 stars, like sun or sun का next star. I think it's Proxima Centauri. Light takes 4.2 years to do that. So that is really, really slow compared to the scale of the universe. And it does put things in perspective. Kitna badi kainat hai. Just our solar system is so huge that Voyager, which was a satellite that we sent back in 1970, I think 70 or 71, early 70s. So that has been traveling for what? 50 years now. और उससे हमें बात करनी अगर होती है, so it has traveled 50 years, but if I send a message from Earth to that satellite, so it reaches it in around 4 or 5 hours. ठीक है? Which means कि if that satellites were to crash, हमें उसका 4-5 hours तक पता ही नहीं चलेगा. Because the only way it's sending us any information is through electromagnetic waves. So the point I'm trying to make here is that light is super slow compared to how big the universe is. Okay? We usually measure distances in light minutes or light years. What distance is kya hai ki how much distance does light cover in 1 second? So this is the speed of light, right? So a light second is simply how much distance light covers in 1 second. So 3 times 10 power 8 is your speed. Distance is 1. So distance is what you need to figure out, and the time is 1. So that is going to be 3 into 10 power 8 meters. So that is 1 light second. If I want to figure out 1 light year, so 1 light year is the distance that light travels in 1 year. So how many seconds is that? So 3 into 10 power 8 is the meter per second, and I multiply it with 3600 seconds in 1 hour, and then I multiply that with 24 hours per day, and then I multiply it with 365 days in a year. So that tells me that light is going to travel 3 times 3600 times 24 times 365. That is this many, 9.46 into 10 power what? 1, 2, 3, 4, 5, 6, 7, 10 power 15 meters. So that is how much distance light can travel in 1 second. Oh, sorry, 1 year. That may seem like a lot. Okay? But let's see how far is the distance to the center of, let's say, the Milky Way, just a small galaxy, a mid-sized galaxy. So the distance to the Milky Way's center, that is around 50,000 times of this distance. इसका मतलब क्या हुआ? इसका मतलब ये हुआ कि light from the sun will take around 50,000 years to get to the center of Milky Way. And Milky Way is just one galaxy. We are talking universe, and universe बहुत बड़ी है compared to this distance. Okay, so distance to the, if I were to find the distance to the edge of universe, the observable universe that we have, that is 46.5 billion light years away. जिसका मतलब क्या हुआ? इसका मतलब हुआ कि आज यहां से लाइट चले तो it will take 46.5 billion years for it to reach the edge of the universe. So light is the speed limit that we have, but the universe is so much bigger. Okay, space travel, if you want to do that, we need things to travel faster than light if we want to make it in a reasonable amount of time. Okay, so that's the point. Anyways, so coming back to what electromagnetic waves are. So despite them being so slow, they're the fastest thing that we have, and they're quite useful. Depending on their frequency and wavelength, we put them to different uses. And the two ideas here are that number one, frequency is inversely related to lambda. And number two, energy is directly related to frequency. Okay, so energy depends on the frequency, and frequency is inversely related to lambda. What this means is, and by the way, this equation can be rewritten as V is equal to F lambda, or this can be written as E is equal to HF, where H is a value, a constant. लेकिन ये O levels IGCSE में नहीं होता, ये IGCSE O levels में होता है. So, but these relations you need to know. What this means is that you can have an electromagnetic wave which can have a very high frequency. If it has a high frequency, it means it has high energy. So if you want energy to be transmitted through electromagnetic waves, just increase their frequency and they will transfer that energy that they have. Okay. So it's a good thing because you can use light to transfer or transmit energy from one place to another. We use it all the time. We use light from the sun. So that is energy coming from the sun to us. Similarly, we send messages using bursts of light in optic fibers, sorry. So they take these light and the light of different frequency, it travels through it and it's able to transmit different amount of energy, और उसको हम convert कर लेते हैं कि अच्छा ये data है, ठीक है? So light से हम उसको use कर सकते हैं. Not just that, I'm talking to you using that. So what's happening here is that I'm talking to this laptop right now, but this laptop is taking whatever I'm saying and this picture and everything, and it's transmitting it as energy and giving it a certain frequency. Microwaves में travel करती है वो, and it goes to the Wi-Fi device that I have at my home. And that way it is transmitted wherever you guys are through these different channels. Fiber optic usually has, it doesn't really have rainbows, like you can't really see because usme se light escape nahi hum karne dete. But if you were like standing inside a fiber optic for some reason, then you will see light of different colors passing through, or you might also see just white light depending on कि इतने ज्यादा different frequencies हैं कि आपको वो सारे mix होके नजर आएंगे. So yeah, that is a good thought. Okay, so that means आपने अगर energy transmit करनी है तो you give it high frequency. But the problem with that is that if you give it high frequency, then it's not able to go a long distance without spending a lot of energy. So that is a trade-off that we have. If you want the wave to travel farther, you might want to give it a greater wavelength, which means you will definitely have to reduce the frequency, which means it will carry less energy. Okay, so that's a trade-off. You want energy, if you want high amount of energy to be transmitted, then you will have to reduce the distances, or you have to boost the wave after some distance. So zyada dur jaane ke liye hum zyada wavelength dhoondte hain. So that is why radio waves or waves that are transmitted by TV channels, or even the waves that are used for like mobile phone and all that, those are the waves that have very low energy, but they have large wavelength. And that's a good thing. We don't want our phones to be using so much energy that wo battery use nahi kar sake, or we don't want a lot of electrical power to be used in transmitting that. So it's a good thing for us that we are able to use it for low energy waves that can travel large distances, right? But if you want waves to, yeah, Zainab, you're right. You're absolutely right. But what your point is that if TIR is happening, then visible light wouldn't divide. But my point was that if light is of different frequencies, it will already have different colors in it, and they're all going through TIR. So red remains red, blue remains blue. But if you're inside the optic fiber, then because there are so many colors, so many waves that you're able to see, because बहुत ज़्यादा data जा रहा होता है, then you will probably see all of them mixed together. Okay, that's what I'm saying. Yeah. So coming back to the idea that if you want wave to go farther, having a large wavelength helps, but that reduces the energy that they need. So that's a good thing, because that is the reason we use large waves for radio, TV, mobile phone communication. But if you want it to travel a shorter distance, but you want to supply a lot of energy, then you might want to consider a wave that has shorter wavelength but high frequency. So that way it is able to deliver a large amount of energy. So for example, if you want to use light to kill cancerous cells, for example, then you need the source to be close so that it doesn't need to travel a large distance, but you will need a high frequency wave. So the electromagnetic waves all happen on a scale. एक साइड पे बहुत ज्यादा frequency होती है, which means there's a very short wavelength and there's a large frequency, and then it keeps on decreasing, increasing in wavelength, and that way you're able to get large wavelength. Okay, but you now have shorter frequency. So the waves that have a really high frequency, we call them gamma waves. Then we have X-ray. Then we have, we can call it X-ray or X-wave, doesn't matter. And after that, there's a small portion in there, a small portion, which goes from 400 nanometers to 700 nanometers as the wavelength. This is called visible spectrum. On the smaller side, the shorter side, you have the blue thing, and on the right side, you have red. And there is green right in the middle. So that is where we get RGB from, the red, green, and blue. Because using red, green, and blue, you're able to cover the whole visible spectrum. And that is why they're called primary colors. So red, green, and blue are the three extremes of this spectrum. Red is on one side, which is the largest wavelength, lowest energy. Blue is on the other side, which is the lowest wavelength, largest energy. And then you have green right in the middle. So there is ultraviolet on this side, then there is the visible portion, Then there's the infrared. Infra means lesser, so it is lesser than red because its frequency is lesser than red. And ultra means higher, so ultraviolet means higher frequency than violet. Then you have infrared, then you have microwaves, and then you have radio waves. And there it's a very fluid scale. It's not like कि अच्छा यहाँ पे visible खत्म हो रहा है और यहाँ पे ultraviolet शुरू हो रहा है और बीच में कोई gap नहीं होगा and all that. So that is true because this is a continuous pattern. और visible के लिए 400 to 700 is an average value. Some people might be able to see a little more than this. Some people are not able to even see this whole portion. उसका भी कुछ smaller उनको लेता है. Similarly, some mammals are not able to see all of it. Some mammals are able to detect greater than it. So some mammals or some plants even can detect light of lesser wavelength than 400, but वो फिर red वाली side उनको इतनी नहीं नजर आती. So we say कि वो इतने red वाला blind है या blue वाला blind है or something like that. Okay, so some people are able to see only a small portion of this, और वो उनको कुछ wavelength detect नहीं कर सकता उनका जो आंखें हैं जो उनके sensors हैं. So we say कि अच्छा उनको selective blindness है. ठीक है. So for example, Facebook, the creator of Facebook, I think he had red green. He had that red green color उसको सही तरह से नजर नहीं आता था. So that is why he chose blue as the color of Facebook. So yeah, it has played some roles. So these are useful. What you need to know, and you can go to the book and figure this out. You need to know the uses of all these. You need to know them in this order. ठीक है. और आपको हर एक का इस्तेमाल जरूर आना चाहिए. जैसे गैमा का एक इस्तेमाल है that it is able to treat cancer. ठीक है. We use it to destroy cancer cells. Similarly, X-ray का use है in medical imaging. You can just pass this through an object, and if it is absorbed by that object, इसका मतलब है कि वो आपको नजर नहीं आएगा, और अगर वो आपको absorb नहीं होता तो आपको वो नजर आएगा. Similarly, ultraviolet is used in tanning beds क्योंकि it delivers a large amount of energy without harming the body as much. ठीक है. Then there's the visible one which we use to obviously see things. Then there's the infrared, which is basically the main source of transmitting heat. ठीक है. There's the microwave which we use for communication, and there's the radio wave which is again for one-way communication. कि आप transmit कर रहे हो, two-way communication भी कर सकते हो उससे. So that's how it is used. ठीक है. So communication में ये सारे use हो सकते हैं. It all depends on what your purpose is. अगर आपने large amount of energy travel करवानी है, तो obviously gamma is the choice, but that means you're giving up on the distances that it can use.
Radiation can cause mutation, which causes cancer. But radiation is also used to cure cancer. How does that work?
So the idea here is that mutations क्या होती हैं? Mutations are when you have some effect on the cellular cell, like DNA है वो आपका break down करके है, या DNA जो है उसके अंदर जो sugar है उनका structure खराब हो गया. ठीक है. जिसकी copy बनेगी तो वो mutation बन जाएगी. ठीक है. Now what happens is that you have DNA, and DNA has these chemicals which respond to light, which respond to these waves that come in. And because they have these electrons and protons in them, and electrons are moving and all that, so if a wave comes in and it can ionize it, okay, so ionizing waves hoti hain, if they have some charge on them and they come in and they can ionize it, तो उसकी वजह से वहां पे electrons आगे पीछे हो सकते हैं, electrons lose या gain हो सकते हैं. ठीक है. Which means कि वहां पर DNA जिस तरह से हमें structure उसका चाहिए वो नहीं होगा. Now, what if you really want to damage the cell? If you want to damage it, then that's a great thing. But if you don't want to damage it, then that's a bad thing, right? It all comes from a perspective. So if you have a cell that you really want to damage because it's a cancerous cell, then you can just put a large amount of ionizing radiation there. Even if you don't want ionizing radiation, आप ये भी कर सकते हो कि आप ज्यादा सारी energy उसके ऊपर deliver करो, and that energy will break the cell wall that it has. इतनी ज्यादा energy होगी कि वो उसको absorb करने के चक्कर में टूट जाएगा. ठीक है. Imagine you have a string and you're giving it energy, you're holding it from one side और उसको आप ऊपर नीचे करते जा रहे हो. So there's a string, यहाँ से वो fixed है, आप इसको इस साइड से ऊपर नीचे करना शुरू करो. If you keep on doing that to a large extent, like we do with rubber bands sometimes, तो क्या होता है, वो टूट जाता है ना, it snaps. So just like that, you have cell walls. वो cell walls या cell membranes जो हैं, वो सारे के सारे इस तरह से अगर आप उनमें एक limited elasticity है, तो अगर आप उसको बहुत ज्यादा एनर्जी ट्रांसमिट करोगे एंड इट्स ऑब्वियसली गोइंग टू बी अब्सॉर्ब्ड, सो वो एक लिमिट तक अब्सॉर्ब कर सकता है, उसके बाद वो डैमेज हो जाएगा. एंड इफ यू ब्रेक द सेल वॉल देन इंटरनल कंपोनेंट्स ऑफ अ सेल दे जस्ट स्पिल आउट, तो वो खराब हो जाएगा. It won't be able to survive. So we can use it if we really want to destroy a cell, we can do that. But if we don't want to destroy a cell, they're a healthy cell, और उसको ये wave आ जाती है, तो वो उसको भी तोड़ देगी. तो the function is the same. It all comes from the perspective. If it's a cancerous cell, you want it to be destroyed. If it's a healthy cell, you don't want it to be destroyed. So काम वही है कि वो एनर्जी ट्रांसमिट कर रहा है और वो उसको अब्सॉर्ब नहीं कर पा रहा, या वो आयनाइज होने की वजह से डैमेज हो गया और म्यूटेशंस आ गई हैं उसके अंदर. ठीक है. So I hope that answers your question. If you're interested, this is a short one-page explanation of this as well. NCBI is a really good website. तो ये थोड़ा सा detailed है, तो you can read it if you really want to. और इसमें वो काफी explain करते हैं. NCBI is an amazing resource for this. खैर, so coming back to waves. Now we know what electromagnetic waves are. We will read about their uses, and now all of these electromagnetic waves are transverse waves. So that means if the wave is going like that, the fields are going perpendicular. That's one. Then they do all sorts of all the 5 things that we talked about. They are all reflected, they are refracted if the material allows them, they are absorbed obviously, they are diffracted if they pass through a slit, they are polarized because they have this perpendicular field, so वो एक field उनका रह जाता है और दूसरा चले जाता है. ठीक है. And they all show interference. So these were the 5 behaviors of waves that we talked about yesterday, and light and other electromagnetic waves all do this, and they're no exception. Like light कोई exception नहीं. हाँ, कोई ज्यादा करेगी, कोई कम करेगी. जैसे रिफ्रैक्शन में हाई फ्रीक्वेंसी मींस हायर एंगल. तो अगर एक चीज की फ्रीक्वेंसी ज्यादा है तो वो डिफ्लेक्ट भी ज्यादा होगी. सो इसकी एग्जांपल आप इस तरह से ले लो, दैट इफ आई हैव अ प्रिज्म एंड लाइट वेव कम्स इन एंड लेट्स सपोज इट्स रिफ्रैक्टेड है, सो ब्लू वाला ज्यादा रिफ्लेक्ट होगा और रेड वाला कम रिफ्लेक्ट होगा. ठीक है. क्योंकि हायर फ्रीक्वेंसी मींस हायर एनर्जी मींस कि वो ज्यादा एंगल बनेगा उसका. ठीक है. सो दैट्स हाउ रिफ्रैक्शन occurs differently for them. Similarly, diffraction में भी वेवलेंथ का रोल होता है. आपके पास ज्यादा वेवलेंथ होगी तो उसका एंगल भी ज्यादा बनेगा. So diffraction is related to wavelength. So higher lambda means higher angle. So ये थोड़ा सा different है. Now this is only for IGCSE, so I'll put a star next to it. In fact, polarization तो दोनों में नहीं है, so I'll just put it in bracket. ठीक है. Okay. So that is how all these waves respond to these 5 processes, and it all depends on the material that you have. So अगर एक material है जो कि dark color का है, that means it's absorbing energy, it's absorbing light, and we talked about it that is why it also feels warmer and it emits heat faster. The reason is the same, that's just absorbing more energy. So वो light है या heat है उससे फर्क नहीं पड़ता है. Similarly, if something is light colored या shiny है, so it's reflecting most of the light that comes in, and that means कि अगर white color है तो वो सारी light reflect कर रहा है, और अगर black color सारी light absorb कर रहा है, and everything else is just going to be a combination of some sort. Okay, so that's it for today.